In this lesson, we will discuss some of what we must know about weighing an aircraft, as well as how to determine the maximum allowable payload for a given flight on a large aircraft, as well as how to determine the length of time a large aircraft must dump fuel prior to landing to ensure it does not exceed its maximum allowable landing weight at touchdown. Additional information on these topics can be found in the FAA Journal Handbook, Chapter 4, and in the FAA Weight and Balance Handbook. The aircraft should be thoroughly cleaned prior to weighing. Dirt, oil, and exhaust deposits will negatively affect the accuracy of the scale readings. The cabin area, engine compartment, and aircraft exterior should all be cleaned. The aircraft should be weighed inside a hangar where wind cannot blow over the surface and cause false scale readings. All of the required equipment must be properly installed, and there should be no equipment installed that is not included in the equipment list. If such equipment is installed, the weight and balance record must be corrected to indicate it. For a list of required equipment, see Federal Aviation Regulations 91.205. All required permanent ballast must be properly secured in place, and all temporary ballast must be removed. Drain fuel from the tanks in the manner specified by the aircraft manufacturer. If there are no specific instructions, drain the fuel until the fuel quantity gauges read empty when the aircraft is in a level flight attitude. If it is not feasible to drain the fuel, the tanks can be topped off. For many aircraft certified prior to 1978, they do not include the engine lubricating oil as part of the empty weight of the aircraft. But for all aircraft certified after 1978, include the full oil as part of the empty weight of the aircraft. The hydraulic fluid reservoir and all other reservoirs containing fluids required for normal operation of the aircraft should be full. Fluids not considered to be part of the empty weight of the aircraft are potable or drinking water, lavatory pre-charge water, and water for injection into the engines. Here you see a sample weighing form. We will use a similar form when we weigh an aircraft as part of this class. One of the common weight and balance considerations for large transport category aircraft is how much cargo can be hauled for a given flight. Here are a couple of terms used in making those calculations. The basic operating weight is the weight of the aircraft, including the crew, ready for flight, but without payload and fuel. The zero fuel weight is the weight of the aircraft without fuel. We will work through an example of how to find the maximum allowable payload for a given flight when we have the following known quantities: the basic operating weight, the maximum zero fuel weight, the maximum landing weight, the maximum takeoff weight, the fuel tank load, and the estimated fuel burn. To find the maximum payload possible for a given flight, we will first add the fuel burnt en route to the maximum landing weight to get the required trip takeoff weight. Next, we will subtract the fuel tank load from the smaller of the trip takeoff weight and the maximum takeoff weight to get the trip zero fuel weight. And then lastly, we will subtract the basic operating weight from the smaller of the trip zero fuel weight and the max zero fuel weight to get the maximum payload. In this example problem, we will use a basic operating weight of 84,000 pounds, a maximum zero fuel weight of 125,000 pounds, a maximum landing weight of 134,000 pounds, a maximum takeoff weight of 180,000 pounds, a fuel tank load of 56,000 pounds and an estimated fuel burn of 38,000 pounds. In our first step, we will add the fuel burned en route to the maximum landing weight to get the required trip takeoff weight. The required trip takeoff weight equals 38,000 pounds plus 134,000 pounds, or 172,000 pounds. Next, we will subtract the fuel tank load from the smaller of the trip takeoff weight and the maximum takeoff weight to get the trip zero fuel weight. Since the trip takeoff weight at 172,000 pounds is smaller than the maximum takeoff weight at 180,000 pounds, we will use it in this calculation to get a trip zero fuel weight of 116,000 pounds. And now we subtract the basic operating weight from the smaller of the trip zero fuel weight and the maximum zero fuel weight to get the maximum allowable payload. Since the trip zero fuel weight at 116,000 pounds is less than the maximum zero fuel weight at 125,000 pounds, we will use it in this calculation to get a maximum payload of 32,000 pounds. Most large aircraft are approved for a greater weight for takeoff than for landing, and to make it possible for them to return to landing soon after takeoff, a fuel jettison system is sometimes installed. It is important in an emergency situation that the flight crew be able to dump enough fuel to lower the weight to its allowed landing weight. This is done by timing the dumping process. To determine how many minutes the crew must dump fuel to reduce the weight of the aircraft to the maximum landing weight, first subtract the maximum landing weight from the current cruise weight to get the needed weight reduction. Next, determine the amount of fuel each engine will burn per minute while dumping fuel. Divide the fuel flow in pounds per hour per engine by 60 to get the amount of fuel each engine will burn per minute, and then multiply by the number of minutes. Then multiply by the number of minutes till touchdown to get the pounds of fuel burned prior to landing. Next, determine the amount of fuel needed to be dumped by subtracting the amount of fuel burned during the dumping process from the required weight reduction. And then determine the time needed to dump this amount of fuel by dividing the number of pounds of fuel needed to be dumped by the dump rate. For this sample problem, we will use a cruise weight of 125,500 pounds, a maximum landing weight of 98,000 pounds, a time from start of dump to landing of 22 minutes, and an average fuel flow during dumping and descent of 2,680 pounds per hour per engine for each of the two engines, with a fuel dump rate of 1,750 pounds per minute. We will begin by subtracting the maximum landing weight from the current cruise weight to get the needed weight reduction of 27,500 pounds. Next, we will divide the fuel flow in pounds per hour per engine by 60 to get the amount of fuel each engine will burn per minute, and then multiply by the number of engines. Then we will multiply by the number of minutes till touchdown to get the pounds of fuel burned prior to landing. Each engine burns 2,680 pounds of fuel per hour, divided by 60, multiplied by 2 engines, multiplied by 22 minutes, equals 1,965 pounds of fuel burned until touchdown. Next, we will determine the amount of fuel needed to be dumped by subtracting the amount of fuel burnt during the dumping process from the required weight reduction to get 25,535 pounds of fuel needed to be dumped to get down to our maximum landing weight. And then lastly, we will determine the time needed to dump this amount of fuel by dividing the number of pounds of fuel needed to be dumped by the dump rate to get 14.6 minutes as the number of minutes we will need to dump fuel to get down to our maximum landing weight.